Good evening. And first of all, in response to numerous inquiries, that very brilliant star-like object in the western sky after sunset is indeed the planet Venus. But this evening, I want to go way beyond our solar system. We think we know a great deal about the universe, but do we? First of all, I'm going to give you a very brief, quite conventional account, and then we'll have a longer, harder look. So here goes convention. The Earth is a planet going around the Sun at a distance of 93 million miles. The Sun is a perfectly ordinary star, one of 100,000 million stars in the Milky Way making up our galaxy, which of course is by no means the only one. Far away, so remote that their light takes millions of years to reach us, we have other galaxies. They're the Andromeda Spiral, more than 2 million light years away, and even bigger than our own galaxy. And that's a member of our local group. Another member of the local group is the Large Cloud of Magellan, where the supernova blazed out quite recently. But that's only a start. Look at this picture. Here we have the Virgo cluster of galaxies, and most of the smudges in that picture are not stars, but whole galaxies, each containing perhaps 100,000 million stars, and around about 50 million light years away. And that again is only the start. What about the quasars? The quasars, look at that little tiny dot there on the end of the arrow. That is a quasar, and according to conventional theory, it's superluminous, perhaps as luminous as 1,000 whole galaxies put together, and is more than 10,000 million light years away, and is receding at more than 90% of the velocity of light. Now, how do we tell that? And the answer is by using the spectroscope and the well-known Doppler effect. Remember, a spectroscope splits up light. And when you look at the spectrum of a star, or a galaxy, you see a rainbow background crossed by dark lines, each one of which is due to some particular element or group of elements. Now, if the light source is moving away, its light appears slightly too red, and that means that all the spectral lines are shifted over to the long wave or red end of the spectrum. That is the redshift, and it is absolutely vital because all our distance measures in the far universe depend upon it. Let's go back again to that quasar. Now, how do we know it is so remote and so luminous? Because of its redshift. The greater the redshift, the greater the distance, and the greater the velocity of recession. That's the conventional theory. But that depends upon the redshifts being pure Doppler effects. Now, just suppose there's some other cause of the redshift superimposed on the Doppler effect. And if that is so, if the redshifts are not pure Dopplers, then all our distance measures may be wrong. And one astronomer who believes that and has observational evidence to back it up is Dr. Halton Arp, formerly of the Mount Wilson Observatory and now of the Munich Institute. Dr. Arp, we're delighted to have you with us. If you're right, then the effects upon all our thinking are going to be pretty profound.
Our entire view of the universe, the size and the mass and the contents, depends on this assumption that we can tell distances by redshift. If that one crucial assumption is incorrect, then our picture falls apart and we don't know very much.
Well, first of all, then, will you give us the observational evidence that you have that the redshifts are not pure Doppler effects or something else superimposed on it?
Fundamentally, the only way you can tell a distance in the universe is to see an object associated with another object whose distance you know. So that if you see objects which are clustered together or are interacting together, you know that they're at the same distance. And if you find that their redshifts are much different, then you know that the redshift can't be a measure of the distance. Now, an example of this we see in this very pretty spiral galaxy with 3 quasars on the edge of it. The quasars have enormously high redshift, and the spiral galaxy has a low redshift. These quasars are so close to the galaxy that they are statistically or probably associated. We see other examples of this. For example, here are 3 other quasars associated very, very close to a galaxy. Now, in addition to these close associations, which are statistically probable, we see quasars actually linked to the galaxy. In this case, the quasar Markarian 205, just below the disturbed galaxy NGC 4319, has a very much higher redshift than the galaxy, which is only about 2,000 kilometers per second. The quasar has about 21,000 kilometers per second. The next example shows quasar of very high redshift, 1.17, and it's connected by a luminous bridge into a disturbed galaxy with a jet that you can see here. The galaxy is, again, very much lower redshift, and the quasar is a high redshift. Now, Not only do we have these quasars of very high redshift linked and associated with lower redshift galaxies, but also we have galaxies themselves of different redshift, which are clearly interacting, but have much different redshift. This is a famous example of one of these. There are many like this known now. The central galaxy is a disturbed Seaford galaxy with a redshift of 8,000 kilometers per second, and the companion, which is linked to it, is 16,000 kilometers per second, much higher.
But are you sure these links are genuine? Could it be any kind of line of sight effect?
The only possibility is that there is an accidental projection of background objects. However, these objects fall so close that the probability is overwhelmingly that they are in fact associated. One of the objects we just saw, the chances was 1 in a million for an accidental association. Another object we just saw, the chances were 1 in 50,000. And there are many of these known.
In other words, there are too many of these cases to be explained away by line of sight effects or just coincidence.
That's right. Statistical investigations of complete samples have shown repeatedly that there are these significant associations. Moreover, they are characteristic of patterns in these associations which are repeated from association to association.
Well, that means, in fact, that the redshifts are not pure Doppler effects, and they're simply not reliable as indicators of distance.
That's right. The only observational test of this assumption that we have shows that the assumption is not correct.
Well, quite apart from that, what about these bridges? How exactly are they formed, and are there any distortions between various systems?
I think a good example is this NGC 4319 object, where you can actually see the luminous connection going from the center of the galaxy to the quasar Markarian 205.
What about the significance of the bridges, then?
Well, I think the significance is very central here, because the bridge goes back exactly to the center of the galaxy. That implies that the material was ejected from the center, and since it's an active nucleus, this makes good sense. Also, we must remember that it's accepted, and it's been proven, that the galaxies eject radio material, and they eject them in equal and opposite directions, so that it's very well accepted and believed that, in fact, as we see here, for instance, an active galaxy nucleus ejects these clouds of radio material, and in this particular case, there is a quasar associated very nearby. In another example, we see this typical radio galaxy ejecting radio material in either direction, and along the line of the ejection is a compact radio source, which in fact turns out to be a quasar of very high redshift. So that, in fact, we know that galaxies eject material, and the only point is what is being ejected. Now, we can see here, I think, one of the most spectacular examples of ejection. This is a spiral galaxy called NGC 1097, and this colored picture shows the long, straight jets coming out from the center of this galaxy. In the next picture, which is a black and white, shows better the contrast in jets. You can actually see a faint fourth jet, again, always the ejection and the opposite ejection, showing luminous ejection of material from this galaxy. But now in this particular galaxy, it's very interesting because there are also radio and X-ray observations. The radio observations are shown here now on the black and white photo. The radio observations are shown in yellow, and they show that the radio material also goes along the line of these ejection of these jets. Finally, the X-ray observations are shown in blue. There are clouds of X-ray material around the nucleus of the active galaxy, obviously ejected from the galaxy, and obviously ejected in the direction of these jets, which are shown here in this picture. But now the really very important and impressive point is that in many of these clouds of X-ray materials, there is a point of light which turns out to be a quasar of very high redshift. These are marked by the X's. And these quasars of high redshift, therefore, are linked to the ejection in this galaxy because the radio material, the optical material, and the X-ray material are all ejected with these quasars.
What about the remarkable galaxy Messier 82 in the Great Bear?
M82 is a very well-known galaxy. It's a very strong radio source. It's a very strong infrared source. It's very disturbed. It's been known for a long time to be ejecting material. You can see it here in the picture. And accidentally, it was discovered that there were 4 quasars very nearby. These 4 quasars are indicated by these open circles, and it's very easy to draw this ejection cone back to the center of the active galaxy, and at the base of the ejection cone you see this little radio cloud. And most important of all, again, if you look at the X-ray observations in this galaxy, you see that the X-ray material is also coming out in this direction of these quasars.
Well, if quasars are being shot out from active galaxies, there might even be some in our local group, which is quite a thought. But now, what about galaxies themselves? Are there cases of galaxies which appear quite clearly to be associated and yet have totally different redshifts?
There are a large number of cases now where galaxies of quite different redshifts are seen to be interacting together, showing that they're at the same distance despite the fact that they have much different redshifts. A famous example of this, a much discussed example, is Stephan's quintet. Here you see the redder galaxies in the upper part of the picture have large redshifts, 5,700, 6,700 kilometers per second. And the blue galaxy in the lower part of the picture has a low redshift, only 900 kilometers per second. And yet you can see the interaction tail of the low galaxy due to the low galaxy interacting with the higher redshift galaxies. Now, something else is very interesting about this picture, and that is that these kinds of interacting galaxies typically occur in the outskirts, in the regions around big dominant galaxies, SB galaxies like our own M31, that dominate a group. So if you look a little ways away from Stephan's quintet, you in fact see this type of SB galaxy. It's called NGC 7331, and it looks just very similar to M31. Around that galaxy, you see other companions like Stephan's quintet, essentially the same redshift, 6,700 kilometers per second. They're obviously associated with 7331. It illustrates the kind of groups which make up space, which I think make up space, big dominant galaxies, and companions around them which have the slightly higher redshift and increasingly higher redshift, but are all located in the same region of space.
Again, you think there are too many of these to be put down to coincidence?
Yes, yes.
What about M31 and M81? They're two of our near spirals.
This follows the development of this investigation of groups of galaxies through to the most impressive point, I think. The M31 group and the M81 group are the two groups that we know the most about. The M31 group is our local group. We know all the companions in it. The M81 group is the next nearest group. We know all the companions there. This visual shows that the biggest galaxy in each group is the SB, M31, and M81. And now all the rest of the companions, which everyone has always accepted as being companions, have systematically higher redshift. The chance of 21 out of 21 companions being of accidentally all of higher redshift is only 1 in 2 million. But on the Doppler interpretation, we should have as many coming towards us as away from us, plus and minus. Clearly that's not the case, and clearly this is a point which is just inescapable. No future measures are going to change these redshifts, and we're not going to find any more companions, so we have to deal with this piece of evidence.
Well, you're certainly painting an entirely new picture. How do astronomers in general view it?
I think that, that there's a great commitment to the assumption that redshifts always mean velocity, and there's a great reluctance to give up this assumption because a lot of work has been based on it, and there is this reluctance to recognize evidence which contradicts this assumption. However, if it's true that the redshifts are not always indicative of velocity, and it's continued to be believed that it is, if this assumption is continued to be believed, then we reach a very critical point in the science of extragalactic astronomy. And this is so important that I think that everybody, every person then has to make up his own mind, exercise his own judgment on this matter, and therefore I think it's very important to discuss the facts of the matter as we have here.
I'm quite sure you're right there. Well, I'm no cosmologist, as you know. Anything beyond the orbit of Neptune is rather a long way out for me. But if you're right, and there is an extra redshift superimposed on the Doppler effect, what's the cause of this non-velocity redshift?
Well, the first point I have to make is that the observations show that the present assumptions are inadequate, so we have to have some other explanation. I think there are a number of explanations which are possible and which different people defend in a very spirited way. That's as it should be. My particular hypothesis, my working hypothesis, my explanation is that the matter which goes into making up these quasars and these higher redshift galaxies is young matter which has intrinsically high redshift, which is ejected from the galaxy and which decays and evolves as a function of time into more normal lower redshift galaxies.
Well, in general, it's generally thought that the high redshift galaxies are a long way away, and the high redshift quasars are the most distant and therefore the most luminous. What you're saying is that instead of being the most luminous, the high redshift quasars are actually the least luminous.
That's the most exciting point for me. If the material out of which these newer quasars are formed has low mass, in the sense that the constituent particles, the electrons and the protons, have lower mass, then their redshift will be high. Now, there's a rigorous theory due to Fred Hoyle and Jean Narlikar that the mass of elementary particles, of the constituent particles, can evolve with time. My application of that to this situation is that it's the evolution with time of the mass of these particles which causes the initially high redshift to decay and become more normal.
In current physics, though, is this kind of creation of matter a possibility?
In past years, it has not been a very respectable thing to talk about creation of matter. And that's a little puzzling, really, because it's had a long and honorable history. The brilliant physicist Paul Dirac, more than a generation ago, talked about the creation of matter. Hoyle and Bondi and Gold talked about the creation of matter in connection with the steady state theory. Andrei Sakharov in 1965 suggested the creation of seeds of galaxy creation this way. So it has an honorable history. However, just recently it's become much more respectable because of inflation theory. Inflation theory is the attempt of physicists to explain the expanding universe by means of fundamental physics, and in that process they conceive of creation of matter. The technical term they use is fluctuations in the material vacuum, and essentially you're looking at a piece of space and the properties vary and suddenly some material appears. Well, why not? My hunch is that the material appears where material previously exists in the center nuclei of galaxies, and that then this material flows out along the bridges or perhaps along the spiral arms. And this particular spiral galaxy we see here, we see that there is a disturbance in the top, in the arm at the top, and if we look in more closely we find a very peculiar blue object associated with that spiral arm, and if we take the spectrum of that object we find amazingly that it has a redshift 1/10 the velocity of light, an enormous discrepancy. This reminds me of the remark that Sir James Jeans made more than a generation ago when he suggested that spiral galaxies perhaps were the place in our universe where matter was poured in from other universes.
Well, that's a kind of cyclic universe. Whether you're right or wrong remains to be seen. It's a fascinating new picture, and of course it does stand or fall on the observational evidence. You presented a case, and now it's up to people to consider it and see what the evidence is. And I think we're going to have some very exciting developments in the near future. We're delighted to have you with us, and I hope you'll be back with us soon. So for the moment, from Dr. Arp and myself, good night.
We urge you not to attempt